Okay, so let's get started. Today we have a fully remote class, and I'm super excited because this is one of my favorite topics in deep learning because it's the type of problems I mostly work at. And yeah, we're going to talk about recurrent neural networks and sequential problems today. And for the next probably like 3 weeks or so, we're going to be talking about sequential problems. So one quick reminder, we have our third assignment due this Wednesday at 11:59 p.m. And the next assignment should be out also on Wednesday, or Thursday morning because it's going to be 11:59 anyways. So you should expect the fourth assignment to be already available on Thursday. Okay, so today I'm gonna motivate recurrent neural networks with sequential problems. Then we're gonna see how to model this kind of problems using recurrent neural networks or RNNs. I'm gonna present the variations of RNNs we typically use and how to train RNNs with backpropagation. So when we do backpropagation with RNNs, we call it backpropagation through time because we're going to be processing sequences. And then we're going to see an important application, which is language models. And we're going to finish with this discussion of exploding and vanishing gradients in RNNs. So I'd like to start with a question. So if I told you that this ball here on the slide is moving, okay, can you tell me what is the next position of this ball? No, right? I mean, it's really hard to guess. Like you can't say, you don't have enough context, right, to answer this question. But now, if I gave you the last the last three positions of this ball, maybe you could guess that, well, this probably is moving to the right. So there are some problems that we need more context, or we need a sequential context to be able to answer or to give a good prediction, right? And there's one that I like a lot, which is this one. Can you tell me right away what is the next letter after T in the alphabet? I don't know about you, but when I need to find the next letter, in fact, I actually have to start saying the letters or thinking about the letters in order, right? So if I see RST, then it's much easier to say U, right? And I like to motivate this lecture with these simple problems. Hopefully that is helpful for you. But if it's not, then here it is. A list of actual AI problems that are sequential. So we have here on this table as the rows, we have a few problems. And then in the columns, we have the inputs and outputs of these problems. So let's start with speech recognition. So in speech recognition, we have an audio as input. It's an audio signal that has someone saying a sentence. And then the output is a sequence of words. Let's say, Alexa, play the Beatles on Spotify. And then we also have sentiment analysis, which is a very classical problem in natural language processing, where the input is a sentence. Let's say, this is a terrible product, if you are in the context of, let's say, Amazon reviews or Netflix reviews or something. Or you want to know if this sentence represents a positive or a negative sentiment. Or you could put this in a scale from 1 to 5. Let's say if it's a very bad review, you're going to transform this sentence into a 1 star only. Or you could have a very good review, have a rating of 5 stars. Right? So you want a model that takes an input, a sentence as input, and predicts a rating out of that sentence. And then you have machine translation, which you probably use very frequently, like Google Translate, for instance. it takes as input a sentence and outputs a sentence as well. But the sentences, they have different lengths, right? So the book is on the table. In English, translates to o livro está em cima da mesa. And these two sentences have different lengths. We also have image captioning, where you get an image as input. And here is not a sequence, it's just like one single example. And you want to output a sequence of words or a sentence that describes that picture. For example, a cat lying by the window. We also have here, not in natural language processing, but in the field that I work a lot with music generation, and in there, normally you don't have anything as input. You want to push a button, and you want that model to generate a given sequence of notes for you that represent a song or any piece of music. There is another one that's probably not as popular, but named entity recognition is this problem of figuring out entities in sequences. So, and entities can be anything, but let's think about this example of we are trying to process texts from the university, and we want to know what words in there are professors and maybe what words are institutions, right? So I want the model to process that text and automatically say, well, this word here is a professor, this word here is an institution. That is very useful for organizing documents and searching in large databases of text. Okay, this is just to say that, well, there is a lot of problems already that are classical problems that we need to somehow use sequential models to solve. So let me now dig deeper in this named entity recognition problem, because I think it's a good way to start thinking about RNNs. So formally, in named entity recognition, we want to locate and classify named entities mentioned in unstructured text. So we might have an input X here, which is a sentence. Lucas Ferreira is a professor at UFV, right? And I want to output also a sequence of numbers, where 1 here represents professor, 0 represents like just general text or ordinary text, and 2 represents a institution. So I'm just trying to find out which words are professors and which words are institutions. We could have this problem framed in very different way with different categories, but here is just 2 or 3 because we have this ordinary text, which is 0. So the way we model these sequential problems is we think about each element in the sequence as one time step. So every element, let's say Lucas, is one input to the model, and then we're going to call that X open or less than 1 greater than, right? We're going to use this notation for representing time step. So the first time step here is the word Lucas, and it outputs 1. And the second time step is 2, and is the word Ferreira, and I want to output 1, and so on and so forth. And in this sequence, we have 7 time steps or 7 elements. And in this particular problem here, we're going to have one output for each input, or for each time step. So we have Y1, which is going to be the output of X1, Y2 for X2, and so on and so forth. So in sequential problems, each input xt can have an associated output yt. Okay, and here is a question for you. Why don't we use MLPs or feed-forward networks for sequential problems? We could model it this way, for example. You could have every input neuron to represent a different word, and you could have an output neuron, every output neuron to represent an entity, and that seems to solve the problem, but why isn't this a good idea? So when you're dealing with text, for example, the sizes of our sentences in English or Portuguese or any other language, they would have different sizes. Let's say UFV is pretty, that's a valid sentence in English, and that's a sentence that we might find in this named entity recognition problem. But then now, all of a sudden, our input has 3 time steps and not 7 anymore, right? So we would have to somehow figure out a way to adjust this network for different sized inputs. And this is another reason for not using MLPs in sequential problems. And the second problem that I'm highlighting here is the one we discussed before, which is MLPs don't capture the temporal dependencies between elements of a sequence, right? So for example, the MLP doesn't know that UFV is a subject here because it's the first element, and it's not going to learn that whatever comes first in a sentence normally is a subject, and then you have a verb normally after subjects, and then you have an adjective after the verb, which is a very common structure of sentences in both English and Portuguese. So an MLP wouldn't learn that sequence or that structure because it doesn't care about the order of the elements in the sequence, okay? So here are 2 reasons, and hopefully that makes sense to you. And in fact, if you try to solve sequential problems with feed-forward networks, right away you'll see that it's actually very tricky to deal with that problem. So without further ado, here is a recurrent neural network. RNNs, they process each input element xt at a time, okay? And the new thing here is that an RNN keeps track of what it's called a state vector, which we denote age t. We can also call this state vector a hidden vector. And that vector is going to capture the context of the elements in the sequence. And this vector is updated at each time step t, or this state vector, okay, to produce an output yt. Let's think about this visually, okay? So at each time step, we have an input vector xt in red here, and this is the first part of this sentence. And then at every time step, we're going to produce a state vector edge t, okay? And this is called the hidden vector or state vector. The first step to produce this edge t vector is to do a linear combination of the inputs xt with a weight matrix wx. So this is very similar to what we've been doing so far. We're going to take this input here, multiply by this weight matrix wx, and sum with a bias vector. This is, you can think of this as a linear model on the input x. But what I mentioned before is, and this is the coolest part of the RNN, is that it uses the previous state vector edge t minus 1 to produce the current state vector edge t. And so we can assume this starts with 0 for now. If you think about edge 0 would be a 0 vector, right? And then you would produce h1 and h2, and you're going to update this vector, so on and so forth, for each of these time steps. So now we are introducing a new matrix, w edge here, okay, that we will use to transform the previous hidden state edge t minus 1. So this is the part that we've been using so far in MLPs, right? This is the z that we typically have in MLPs. And this is the new part we are adding, which is we're going to keep track of this edge vector at each time step, and we're going to update it based on the previous state and the current input. Okay, so you can think about this vector as a compression. So the edge vector kind of compresses the information that the network has seen so far until t minus 1. And then we get a new input, edge xt, and we're going to combine these two things to form the new hidden state. So at every time step, the network is condensing or compressing the elements it has seen so far. So at the end of this t time step, the vector edge has all the information so far until time step t condensed in a dense vector. And the size of this vector we can define ourselves, okay? This is a hyperparameter of the network. So that's the formulation. The only thing that is missing here is a nonlinearity. So basically you just plug a nonlinearity to this formulation and that's it. And that's your edge t, okay? And then we're going to use this edge t to produce an output. Okay, because as I just said, this edge t has all the information so far. So if you had 4 time steps and we are in the time step 3, edge of 3 condenses the information of edge 1, edge 2, and edge 3, or x1, x2, and x3. Right? So it has the summary of the sequence so far. And then we just have a new matrix here now, and we have this weight matrix wy, which we multiply by the current hidden vector to produce our prediction at time step t. So, and edge 1 is a hidden layer, activation function of the hidden layer, and g2 is the activation function of the output layer. And in practice, we use tanh or ReLUs for g1. Historically, tanh is more common. And for output, then it depends, right? It depends on what problem you have. So if you have a regression problem, you would use just a identity function. But if you have a classification problem, you would have a sigmoid or softmax. Like the named entity recognition problem, you would have maybe a softmax as G2 because we have many entities and their classes. But if you have a binary problem, then you might have a sigmoid as an activation function for G2. And this is it. This is a recurrent neural network. And the only thing you've added is this hidden state vector, and we use it to produce an output for each time step. Is this clear? Any questions? Another way that people normally show RNNs is through this kind of circuit diagram type of thing, where here I'm actually increasing the size of the RNN hidden layer. So if you still are confused about what is an input and what is a hidden and what is an output layer, so the input layer is the examples you receive, right, over time. So now the input layer kind of unrolls over time. And your hidden layer is shown in green here. So for each time step t, we get an input vector x and a previous hidden state t minus 1. Okay? And I'm just going to show the same formulation, but now visually. So the first thing we do is we multiply the edge t minus 1 by this weight matrix w edge. And then you do the same thing with with another weight matrix wx, right? You multiply it by the input xt, and then you sum both of them, okay? And then sum also the bias term. You apply the nonlinearity to that result, right? And then you produce the next hidden state, ht. So if you look here, right, this is g1 of, there is a plus here, right? This plus is this 2, representing these 2 pluses here, right? I'm summing this term, w edge t minus 1, right, which is this part. And then this second term here is this term at the bottom, right? I'm summing these three terms. So this summation here represents these two sums, and applying the nonlinearity, and then I get edge of t. And this is the hidden layer. So the goal of the hidden layer is to update the hidden state, edge t. And so the output layer is given by this wy matrix that is multiplied by edge t, right, producing a prediction. This is very common also when people are showing RNN, so I wanted to put it here as well because you might see this kind of diagrams online when you're searching for RNNs. Okay, so this time I'm not seeing you, all of you, so please interrupt me if you have questions, okay? So another way that is useful to look at RNNs is unrolling them over time, okay? Because right now, the way we defined it is recurrent, right? So we have this recurrency over each time step t, but you can unroll these this recurrency over time. Let's consider a sequence of capital T time steps, okay? So then you would have x1, x2, x3, dot, 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 xt, right? So you have at the bottom here, T time steps, each one has its input x, right? We're gonna start with the very first input that's gonna produce our very first hidden state, h1, right? And then we have to start our h0. This is normally started with zeros. Okay, so you pick, let's say, a dimensionality for the hidden state. Let's say it's 10. So you would have a vector with 10 zeros here. And that dimension is going to be carried over the whole network. Okay, so if this edge 0 if you started with 10 dimensions, all your edges, edge updated versions would be also with 10 dimensions. So we're going to produce an output y hat 1 and also update h1, right? So I'm just showing here that this arrow is sending h1 to the next time step, okay? But now, and this is updated with this equation, right? So we have h1 equals to g1 and w edge h0 plus wx x1 plus b edge. So this is the edge 1, okay? And h0 is just 0, okay? So, and these matrices are started randomly, as in MLPs. Your x1 really depends on your input, and then your bias term also is going to be, normally is initialized with zeros, you can initialize it randomly as well. Then you produce the output with this equation as we just saw. But I'm just showing them over time now, okay? So the second time step, you would process x2, but now you're going to use edge 1 here to produce edge 2 and your second prediction, right? And this is your equation now. You have h2, which is you're going to use edge 1 from before. See here, so this edge 1 that was defined here, right? And x2. Okay, but see that these matrices are the same, okay? So all these three matrices are the same. I don't have different set of matrices for each time step. And we keep doing that until we reach the end of the sentence, okay? Let's say the sentence has t time steps. So in general, we can write this using that equation, right? Ht equals to g1 w edge t minus 1 plus edge x xt plus b edge. Okay, and then y hat t equals to g2 wy edge t plus by. But yeah, I just want to really point out that these three matrices are shared across all time steps, okay? So in code, you can imagine you have your init function there. You're going to start 3 weight matrices for your RNN only, and that's it. And their sizes, as usual, the WX matrix depends on the input, the WY is going to depend on the output, and this W edge is going to depend on the size of your hidden state, which you're going to define as a hyperparameter. In the assignment, you're going to implement this. So exactly this model. So there is going to be a place for you to really work with these equations and make sense of them. So let's see the different types of RNNs we have. So far we've been talking about this many-to-many RNN, and we call it many-to-many because we have many inputs and many outputs. Okay, one output per time step. And this is the case of named entity recognition, right, where you have to output one category of entity, right, for each word in the sentence. But different problems have different setups or different types of inputs and outputs. So in machine translation, which is also a many-to-many problem, we have a different setup because the number of inputs might be different than the number of outputs. And this figure is not probably the best figure because I should have actually have 3 at the bottom, maybe 2 at the output at the end here, at the top, because a sequence, let's say in Portuguese, when it gets translated to English, right, you keep the meaning, but the number of words might change. Right, the book is on the table, doesn't have the same number of words, then o livro está em cima da mesa. So it's slightly different, but it's many-to-many. And we call this model sec-to-sec because we have a sequence and we are as input and we are producing another sequence as output. Another one is many-to-one. In this case, we have many time steps in the input, but only one output at the end. Okay, and this a good example is sentiment analysis. When you are computing the sentiment of a sentence, and let's think about a binary sentiment analysis, you have either positive or negative sentence, you need to process every word in that sentence to produce one output, right? I need to know, like, this is a terrible product, right? So when I finish that last word product, then I'm ready to say, oh, this is a bad or a good sentence. Because I don't know, maybe the last word is the word that gives the whole bad or good meaning. Right, so we only give prediction at the very end. We kind of disregard this previous outputs here. We don't look at them. And we also have one-to-many. For instance, image description. If I had an image of a cat and I wanted to say, oh, this is a cat lying by the window, I have an image as input, and this image somehow has to become a vector. And then I have to output a sequence based on that single input. Okay, and that's another configuration that you can have with RNNs. Another one is one-to-one, sorry, this is wrong, which is just an MLP. In principle, so you could reduce an RNN to an MLP if you wanted. Okay, so, and I'm going to also introduce the losses here as we discuss these different types of RNNs. So let's look at many-to-many RNNs. And here let's assume the problem of named entity recognition just to make it easy to understand what's going on. So you would have this example, Lucas Ferreira is a professor at UFV, which is a sequence that has 1, 2, 3, 4, 5, 6, 7 time steps, and it also for each time step, right, it has an output. So 1, 2, 3, 4, 5, 6, 7. So this is the type of structure we just saw, right? This is the first one we looked at. There's nothing different here, right? I start with an H0, that is 0, and then I have my inputs here. At every time step, I produce a hidden state, which is used to produce the output y hat t, okay? And the equations are just the same. There's nothing, literally nothing different here. The only thing I'm adding is that for each time step, you'll have a loss. So somehow your data set would need a pair of sentences like this, and the ground truth named entity recognition, named entity annotated there for that particular sequence. So then you could compare your prediction against the correct one and somehow calculate a loss, okay? Yeah, the way we compute the loss for this example is we're gonna have one error for each of these time steps, okay? So basically imagine if I started my network randomly, I could have an output which would be 0, 0, 1, 0, 1, 0, 0. And then, but the ground truth is this one. So I have to compute the loss between my prediction and the ground truth. And the way we do that is summing the losses for each time step. Okay, and that's the error of the whole sequence. And then we're going to do backpropagation over that error. And I'm not highlighting which exact loss function to use because that depends on the problem. Okay, for named entity recognition, right? You could have a maybe a softmax output at the end, and then you could just use categorical cross entropy for each of these time steps, and then sum all this error, and that would be your total loss. So magnitude 1. Now, again, we have a sequence of words and 1 sentiment as output. And here I have a rating from 1 to 5. Sentiment analysis can be modeled in different ways. As I said, it can be either a binary problem of positive and negative sentiment, but it can be a regression problem. Here you would have a number between 1 to 5. So even though I'm showing stars here, you could have a prediction of 3.7, for example, or 4.2. Right? And then you could just show it as stars if you wanted. But here we start our edge 0 with 0. And the main difference is that we just look at the very last output. Because to understand if a sentence is bad or not, I really need to look at the whole sentence, right? In this case, particularly, the third word or fourth word here is actually the most important word in this example, right? Because if I changed it to good, then it would change the whole output to maybe a positive sentiment, right? So if I had this is a good product, then the output should be 5. But since it is the word is terrible here, then the model should predict a lower value. And the model can only know that because it processed the whole sentence. If I had this sentence, then it's more explicit that I do need to process all the words to know that this is even worse than the previous example, right? This is really terrible. That one was just terrible. This is really bad. So if I process only this is really, I don't get anything. But as soon as I process the last word, I know that this is bad or good. So we just look at the prediction of the very last time step, a y hat of capital T. And here we have only one prediction at the end. So let's say this could be a number, if the ground truth here is 1, maybe my output in the beginning was random, maybe I predicted 2.5, then I compute the error, 2.5 minus, maybe I can use a mean square error, right? Compare my output against this 1 here, and then update my weights based on that error. All right, one too many. This is interesting because now it starts to get different. Consider this problem of image captioning, right? You have an image as input, right? And then you want to output this sequence that describes what is in the picture, right? So here we have this image X, and we're going to use this image to initialize our hidden state 0. So we are giving to the model this hidden state and we are conditioning, let's say, the model to start processing the sequence from an input. So imagine we flattened this image and we made our edge 0 our first hidden state, which is just the image, right? And then we follow the same process. We update edge 1 based on this edge 0 and then predict a word here. Let's say A. And then we update H1 with H2 and update another and output another word, cat, and so lying, blah, blah, until we get to window. And then for each of these words, we're going to have a loss, and we are trying to predict the right word here, right? So the cool thing here is that you can initialize H0 not with zeros, but with a previous context. right? And which in this case is an image. And RNNs can learn this problem by outputting one word at a time, which is really nice as well. Quick comment. I didn't say it here. I'm actually just saying half the truth here for you. Because in practice, people wouldn't do just this, right? They would probably feed this image to what is called an encoder. They wouldn't directly flatten the image and put it as a hidden state, mainly because that's then you end up having the problem that we discussed in the CNN lecture, which was so the larger this image, the larger would be your hidden state, right? And you don't want that. And also, when you just flatten your image, you're losing your spatial dependencies that you have in the image, or a spatial structure, right? And so it's not a good idea to flatten your image. So in general, people would have a CNN here. They would feed that image to a CNN, to a sequence of convolutional layers, get one vector, a more dense, smaller vector at the end of that CNN, and then use that vector as a hidden state, okay? I don't want to put that in here because that would bring a new discussion, but in practice you would have an encoder which would transform this image using a CNN. Something that we haven't discussed is that actually now I don't have an input for each time step because my input is just an image, so I don't have the x1, x2, x3, and xt. So what we do is we start our x0 as what we call y0, and you'll see why we are using y here. Think about y0 as a special start token. Okay, I'm going to write it here so it's more clear. Okay, so imagine there is a start token here before a, which is a special word we just created that represents beginning. Okay, and then we feed that, and we do that, we include this token before training. So imagine we include a start token in the beginning of every example and a end or final end of sequence token at the end of every sequence in our data set. So if we start with this start token, we're going to be following the representation and the structure that we have in the data set. But we feed that as it was our x0 to our hidden state, to our hidden layer that's going to take h0 that represents the image and that start token. So based on these two information, it's going to predict a y hat, which should be hopefully the letter A, because after the token start, the article like A is probably a good guess, right? So then what do we do now for the next ones, right? So we don't have a x1 here. So what we do is actually this. We take the output of the previous time step and make it the input of the current one. Because now we are conditioning this second time step with the output that we produced before. So in this case, if you're making a mistake here, then yes, most likely you're going to keep making mistakes after your first step. But that's not guaranteed. By chance, you can still make one prediction right here, but you're going to do that until the end, and we're going to make then our xt inputs to be our y hat t minus 1. This should be y hat. Okay, this is a trick that we use to decode. We call this a decoding process, to decode this image as a sequence. Okay, and we do that step by step, and then our prediction at time step t is going to depend not only of our previous hidden state, but also on our previous output. Okay, this is like translating one word at a time. Think about if you would translate a sentence, you normally write one word at a time, right? So, and the second word depends on the first, and the third one depends on the previous two. So this is kind of simulating what we do when we write. We write from left to right, and we write one word at a time, and each word depends on the previous ones, okay? Let's move on. Yeah, and loss in this case is also computed summing the losses of each time step. Let's move on to see sec-to-sec models, okay? In here, the principle is the same. We have to initialize our hidden state. But now instead of using an image, we need to initialize it with a sequence. So sec-to-sec is mainly used for this kind of translation problems. So think about machine translation, Google Translate, for instance, right? You have a sentence in English, you want to translate to Portuguese. So what you have as input here is x1, x2, and x3, and xt. Here should be, for example, the book is on the table, for example. And you want to translate it to o livro está em cima da mesa. So the way we see these models is we see this as two independent networks. We have the encoder network and the decoder network. So here I'm showing that this encoder network has these two set of matrices. And this decoder also has its independent set of matrices. So they are really two different models. But what we do here is we start with the encoder. We want to encode, right? We want to build a vector that represents the input sentence. The book is on the table. So you want to summarize that sentence, the book is on the table, on a single hidden state vector. What you're going to do is we're going to process the and then produce edge 1. And then book and then produce edge 2. And then is and then produce edge 3. Until table, which is the last word, and that's going to give us the hidden state edge tx. And I'm using tx here because the number of elements in the input sequence might be different than the number of inputs, the number of elements in the output sequence. So I'm using tx and ty here. So at the very end of the encoder, what you have here is a hidden state vector that summarizes the whole input sequence. So here you can imagine a vector here that represents the whole input sequence. And then we follow the same decoding procedure as we just saw in the previous slide. We initialize the sequence with a start token, like a special token. But now we have this condition here, which is this hidden state that came from the encoder that represents the input sequence. And then we're going to produce edge 1 and predict a word. Hopefully it's going to be O, right? And then now we pass edge 1 and see that we are continuing here. Edge 1 now is continuing this hidden state. Okay, I'm not resetting here. I'm actually updating this hidden vector to produce a word O, for example. And then now I feed that as input to my next time step. So I use the word that I predicted before with the information that I've used so far. So at this point here, this is very interesting. At this point here, the hidden state vector not only has information about the whole input sequence, but it also knows some information about the current translation so far. So it knows that the input is the book is on the table, and it also knows that the first word that was chosen was O, right? And then it repeats the process. Now updates the hidden state and outputs, hopefully, livro, right? And then it keeps doing that until you reach the end of the sentence, which normally, in practice, what we do is, again, using that special token EOS, end of sequence. And if you find the token, then you are done with decoding, and you can compute your loss, which again is just summing the losses of every time step. Okay, is it clear that this is the same thing as before, but now we have, instead of having an image as input, we have a sequence as input, and we are using an encoder. If you had an image here, your encoder would be a CNN. But since our input is a sequence, we use another RNN to produce a hidden vector. All right, this framework is very popular and is very generic. Like any problem that you can imagine that can be thought of a translation, right? You could use this framework. It doesn't have to be a translation in the sense of words in languages, but it can be any. If you have a sequence and you want to translate that sequence to another domain that is also a sequence, you could in principle use this kind of problems. Right? I think this kind of relates to, so Felipe is working on a problem, right? He's my student and he's working on this problem of generating soundtracks for videos. So a video is a sequence of frames, right? So you would have an encoder that would process those frames, produce an output here, and then your decoder would somehow generate music step by step using that vector that represents the video. So this problem has nothing to do with languages, but it still can be thought as a machine translation problem. All right, so we are not gonna do backpropagation for RNNs like by hand, but I want to give you the intuition of what's going on. So we have many time steps here, right? So the way we train these models is by first processing all the T elements or the T input elements, right, of the sequence, and then we calculate this loss, which is the sum of the losses of each independent time step, and then, right, we backpropagate through time, because time is the x-axis, right? So you're going to backpropagate through time to calculate the gradients. And what is tricky here is that to update the weight matrix for this very first time step here, we're going to this is going to be affected by the whole sequence, right? Because think about this, right? I'm starting W0 here and H0, and then this is affecting all the computations here, all the way here to get here, right? So when I'm backpropagating, I'm flowing the gradients backwards all the way to here, okay? Because I need the loss function, I need the gradients, right, of the loss function with respect to W0. And this is really tricky in RNNs, because especially if you are processing long sequences, then it makes it really challenging to train these models, because we need to update the weights over time like this. And in practice, because we might actually have very long sequences, so consider, let's say, a Wikipedia article, right? If I wanted to train a language model that predicts the next word given a context in Wikipedia, ideally I would have to process the whole document and sum the losses of each word to update my model. But because that document can be too large, what we do is actually what we call truncated backpropagation through time. So what you're going to do is pretty much, you can think of this as kind of mini batches, right? We're going to update our model after every j number of time steps. And here I'm using j equals to 4. So basically, I'm going to do a forward pass here, sum the losses, and then update the weights. Okay. Then I'm going to move that window 4 steps forward and do the same. Okay. In this case here, we would carry the hidden state from this mini batch to this mini batch here. Okay. So because even though we are treating this subsequence here as an independent problem with respect to the previous one, we could just share the hidden state, because this hidden state actually has information of the previous sentence. So it helps making these predictions more correct, because we're not going to lose the whole context from before. Right? But then, yeah, you would process the next 4 examples, sum their losses, and then do backpropagation and update the weights. So now we updated the weights once, and then just updated the weights another time, and then we do that for every chunk of size 4 in this case. It doesn't have to be 4, right? You can pick any size you want, and also depends on the size of the documents you're trying to process. Nowadays, with these large language models, they are being trained with like crazy amount of data, the whole internet, if you want to imagine it, the size of this thing. So it's impossible to fit the whole internet on the GPU, right? So you do have to do this. You have to truncate your backpropagation and train after every, let's say, after every document or every paragraph, so something like that. So you have to subdivide your problem into minimal problem, or smaller problems, and keep updating your weights this way. Again, these updates will be noisy, but because we have many examples and the data is huge, this is going to actually converge to a model that actually learns your data. Let me see what time is it. Oh, okay, we are at the end. Okay, I think I'm going to stop right now, because there's still like 10 slides, I guess, to finish this lecture. So I'm going to stop because we are at the end already. And then we finish on Wednesday, and we're going to use the rest of the lecture to talk about GRUs and LSTMs, which are just more fancy RNNs. Okay, thank you, and I can take questions.